Rate of change is an important concept when thinking about analyzing functions. We can think of rate of change as basically the same idea as slope, or how y is changing. The output of our function is changing as x, the input of our function, is changing. So if we look at something simple like this linear function, we have a slope of 2/3. Okay, that's our slope there, meaning that every time x increases 1, our y is going to increase 2/3 of a unit. So we can see that on the graph here. This purple line represents that function. And you can see we have a slope or a rate of change of 2/3. You may have learned this as rise over run. Rise 2 for every 3 we run. Or as we move forward 1 unit, we go up 2/3 of a unit. So we have a positive rate of change here. You can see as x increases, y increases. For this function, we have a negative slope. As you can see, we have a slope of -3, or you can think of it as -3 over 1. So that means as x increases, so as we move to the right, our function is decreasing. So you can see there's our negative slope. The line is moving down as we move to the right. And again, we can think of this as rise over run. We're going down 3 for every 1 we run. However, when we think about nonlinear functions, so as we start to look at curves, our rate of change is going to change. So here we have a piecewise function where we start out with a constant rate of change over here in this linear section. But then when we look at the quadratic, the idea of slope gets a lot more complicated. We have a negative slope at some points, we have positive slopes at other points, and even that positive slope is going to continue to increase and increase. So our rate of change is increasing. So often when we analyze a curve, we'll think of not just the rate of change at any given moment, but the average rate of change. So any sort of curve like this one drawn here, we can pick 2 points and then find the slope or the rate of change across that interval. So we can connect those 2 points, any 2 points on a curve. We can connect them with a line. We call that the secant line. The secant line connects 2 points on a curve. And then we can find the slope of that line. So if we find that slope, what we're going to get is the average slope during that interval. As you can see, this slope is negative on average, but it doesn't mean the slope is always negative during that interval. As you can see, it starts out with a positive slope and then a 0 slope and then becomes negative. So we want to be careful with our language. When we are talking about average rate of change, we want to make sure to include that idea of average. On average, we are decreasing as x increases. To find this slope, we can use our slope formula, which you can see here. The slope of the secant line is equal to f of x2 minus f of x1 divided by x2 minus x1. You may have seen this slope formula in a slightly different version, y2 minus y1 over x2 minus x1. Okay, so it's not quite as complicated as it looks in function notation. Again, what we're thinking is how does y change as x changes? What is the change in y compared to the change in x? This is the delta, means change. Okay, how does our vertical displacement change in relation to our horizontal displacement? Okay, let's look at a couple examples. For this one, we have a little story problem here. We've got the average price of a movie ticket in America for different times. So in 1995, a movie ticket on average cost about $4.35, and you can see it's increasing. Okay, so they're asking what is the average rate of change between 2003 and 2021? So I've got those 2 data points right there. And we can use our average rate of change formula to solve this. So I need to figure out, okay, what was the movie ticket price for our second time? I'll say this is time 2, and this is time 1. Doesn't really matter which one's which. And then what is our movie ticket price for time 1? And along the bottom, we're just going to find the difference in those times. So again, we are looking at change in output divided by change in input. Usually that's y and x, but you can see this time it's a little different. We have t as our input, and then our output is called m of t. Okay, so the time is easy. We've got 2021 to 2003. And on top, we've got the price for a ticket in 2021, $10.17, minus the price in 2003 is 603. And if we simplify this, so solve the top, solve the bottom, and then divide, we're going to get 23 cents per year. Okay, so $0.23 per year. Notice the units here when we think about slope is going to be the Y unit per X unit. So what we're seeing here is the price of a movie ticket has been increasing 23 cents per year on average. So again, be careful with your language. We didn't just go up 23 cents. You can see we went up more than that, about $4. But every year we went up about 23 cents on average. Again, it doesn't mean we had a steady, constant increase. We don't know if it's linear or not. Maybe it is, but it's not. But on average, we are increasing about 23 cents every year. Let's look at another example. This time, this is from your homework. So we have this function f of x, and we want to know what is the average rate of change on this function over the interval from 3 to 6. Okay, so these are both x's here. From this x to this x, what is the average rate of change? Okay, so we're going to find our average rate of change, also known as slope, across that interval. So to do this, I'm going to plug in 6 to figure out what is the output at 6, or what is the y at 6. Do the same thing for 3, and then I'm going to find the difference. So what is the difference in outputs between 6 and 3? On the bottom, we'll look at our difference in inputs from 6 to 3. Now, actually plugging this in is going to be pretty intensive. It's a lot of work, right? We have a pretty nasty function here. So I'd encourage you to use Desmos. So you can see on Desmos, I've got, sorry for the flicker, I've got this function put into Desmos. And then because Desmos understands function notation, we can just slip that into there as long as we've got our function put in correctly and we've set up our problem correctly. We can avoid some of that tedious arithmetic and just get straight to our answer. So you can see we have a very, very negative decrease between those points. And you can see that on the graph. You can see how quickly the graph is dropping here. So we are decreasing about 2,500 units in the y direction. So every time we go 1 unit forward in the x direction, we are decreasing negative 2,550 units in the y direction. So a very steep drop. Remember, this is an average drop across that interval.